you hear me?
So, hello everybody, and welcome to this nice conference, use of R in official statistics. I hope you hear me quite well. So we'll have now the second scientific session with the name classification. And we'll have here 4 speakers, 4 presentations. So I will kindly ask you to have the presentation in about 13 minutes in order to have 2 minutes for Q&A. And then at the end of the session, we will have lightning talks with about 5 minutes per talks per presentation. So I'm Ciprian Alexandru from Romania, from National Institute of Statistics and from Ecological University of Bucharest. And thank you for all organization. Thank you, Alex. Thank you to all my colleagues. And from my side, I would like to wish you a very nice conference. So let's start with the first presentation. The name of the presentation is Classification in R, and the presenter is Susie JENTOFT from Statistical Norway. So if you are ready now, Susie, you can share your.
Great, thank you.
Just 1 second. Let's see.
I think it should work already, Susie, right?
I think it should work.
Yeah.
Okay, thank you. I'll see if I can start that.
Okay.
Perfect. So my name is Susie, and I work at Statistics Norway in the methods department there. And we are a group of people that work on both statistical methods and survey methods, but we also have a role in terms of maintaining R in the organization. So this talk that I'm going to be giving is relating to the use of classifications within the organization and an R package that we created in order to access these standard classifications in an easier way. So the use of standard classifications is perhaps not the most exciting theme that everybody thinks about. There isn't any fancy algorithms or text analysts that I imagine some of the next talks will be about. But in terms of using standard classifications within a statistical bureau is very important in terms of harmonizing data sets and statistics across divisions. So just as an example of what I'm talking about here, this is how our system used to look, or perhaps in some areas still does look, in terms of coding of sex within Statistics Norway. So within some divisions and some statistical databases, we may use a coding system of 1 for male and 2 for female. However, there were some groups, particularly those that were quite feminist, decided that no, male shouldn't be number 1 anymore. We would like to use 2 for male and 1 for female. So some databases and datasets will use this. We also have some people that use 0 and 1 for male and female. We then have some that use letters, so M and F for male, female, or male and woman. The Norwegian word for woman is kvinne, so sometimes we'll see M and K, or small letters, big letters, the full words, etc. We also have some that use an unknown category. This could be the next number 3, it could be 9. There may be some surveys where it's a refusal, so there's all sorts of different coding for this. So in the case of sex, it's perhaps not the biggest problem. You can just, sometimes you can probably deduce it. Other times, for more complex variables, it's important to know what the coding system is. And if we're going to share data sets between divisions and combine different data sources, then it is much easier if we're all using the same coding system. And so in order to do this, we generally need to decide on a standard. So within the organization, the standard for male and female is this first one, 1 and 2. So the question is, how do we get people to use this standard? And that's where a system called CLASS came in. For us, it's Statistics Norway. And this is a database for documenting and maintaining statistical classifications and code lists. So this was created a number of years ago now. And it's both a website, so everybody within the organization and outside the organization can access all of the classifications, both the ones that are current and the ones that are previously been used. There is also an API access to this using a REST API. So it's possible to send in queries to this database from a computer, and then you get the full classification back. And this is based on the GSIM model, so the Generic Statistical Information Model. The question is, though, we have had this database for many years, but in terms of how do we combine this, how do we use this with R? So previously, we would have perhaps gone to this internet site, and we could do a query, and we could save the query. We could then copy it into R, and then we could send it. If we wanted to do repeats of this, we could send it, and then we would read back a JSON file, for example. So in some cases, people would just go to the website, then they would download a CSV of the standards, then they'd read the CSV into R. But it was a little bit, it could be time consuming, and if you weren't particularly knowledgeable with the system, it would take a reasonable amount of time. So we decided to have a hackathon project. So this was a short, intense 3 days with a group of people to come up with some functions that we could use in R, where we wouldn't have to be swapping between environments, where everything could be done within the R environment in a way that was familiar to our users. So we developed during this hackathon, which was back in, I must say, back in 2018, we developed 3 functions. They were around searching this database, around getting the classifications, and around applying. So these are the ones that I'm going to talk a little bit about further today. And then I also want to mention about marketing of the package. So each classification within the system has a specific number which is unique for that classification. So in order to find that number, you can go to the website and look it up. But we created a function called search class, where instead of leaving the R environment, we could use this to find the classification and the classification number. Function get class fetches the classification in its full form, or apply class can be used to apply a classification to a variable or a vector. So the first one of those, search class, this is an example of how it looks. So search class, and then you can just put a keyword or several words in. So here, for example, is municipality. And it returns a list of possible classifications that might be relevant, and then their unique classifications number. So this, this is very useful in terms of if you've forgotten, perhaps if you know that there's a classification for the county municipalities, but you've forgotten which number it is. It's a quick function to be able to find that out. The classifications are listed within several languages, so this can be used in both English and the 2 Norwegian languages, and it should come up with the required results. The next function, getClass, so this returns the full classification. So for example, this is an example for occupation codes. So that is class number 7, so that's specified first. And then other things that can be used in terms of the parameters are language. So for example, English is EN, or Bokmål is NB. You can also specify a date. So all of the classifications are date stamped. So each classification will have a start date. So if you're looking for a classification that is no longer used, but was previously used, and perhaps if you're working on older data sets, it'll be important to match up the correct classification. By putting in 2 different dates, you'll get all of the classifications relevant during that whole period of time. And there's also a correspond option whereby you can get the changes. So that'll just list out what, if there's been additions or changes to the codes, which can be very useful. So within the database, some classifications, when they change, they will change with a date point on them. However, some classifications will change in terms of the overall classification code, that unique code number, in which case we create also correspondence tables. So this is generally between different versions of standard classifications, but some classifications do create new versions for each time. So there is some, it's not completely standardized between our standard classifications. However, these correspondence tables are particularly important, for example, in occupation, where we have some divisions reporting for one version of the occupation codes, whereas that's the case for example, our administrative data on employment, whereas, for example, our labour force survey uses a different version of the occupation codes, in which case we can use these correspondence tables. The final thing was apply class. So this is, we identified 3 needs that are often useful in terms of our data sets. So for example, if we have a data set, here's some standard industry codes. One thing that we may want to do is relating to grouping or recoding. So we might want to find out for these standard industry codes, which is the main level of industry category. That's not always easy to determine strictly based on the code, so we can wanted to use this apply class to be able to fetch out the industry group.
Okay, Susie, you have 2 more minutes. Please conclude. Yeah, thank you.
Okay. So the other thing is relating to the names. So for example, figures. If we want to create a plot, it can be useful to take out the names. And again, converting. So we use this apply class for that. And again, we can use language to decide whether we want it in Norwegian or English. So the final thing is to do with the marketing. So it's one thing to build this great system, but And if you want people to use it, you need to be able to find ways. So we've now incorporated it into, for example, our introductory courses and our data cleaning courses. It's on CRAN. We use it, mention it in our forums. And the latest thing in terms of having our leadership on board as well, encouraging and even making sure people use them. And the final one is that we've also created now an e-learning course using LearnR and Shiny. So this is an interactive tutorial that takes people through examples, and then they also have little tests and things that they can complete on this online tutorial. So thank you. That's what I wanted to talk about. But the main thing is that it requires repeated encouragement for use. It's not enough just to create some really good functions that will take up these standards, but also find different ways to encourage people to use it to increase the use of standards. Thank you.
Thank you very much. It's a very important issue for statistical offices to use good classification. And personally, I appreciate that you share with external entities your work. So it's very important because also they have to understand the classification when they produce some data and we collaborate in exchanging the data. So thank you. If there are any questions until now, let's see. It's only one question from Olaf. Did you maybe consider to connect to their classification requires such maybe SDMX registers from Eurostat?
Yeah, I haven't looked into this actually. The system includes both sort of international and internal, and in order to have all the Norwegian names and things, it was important for us to join up to our internal system. But yeah, no, it could be interesting to look at the external, the Eurostat one as well. It's a good suggestion. Thanks.
Thank you. Thank you. So I can thank you now, Susie, for your presentation, for everything, for closing, because you are so close to our conference by so many years. So thank you for all your contribution in our community. I will change now the presenter. And the next presentation is Julia LITOFCENKO with a presentation methods for classifying non-profit organizations according to their field of activity. A report on semi-automated methods based on text. So Julia, you can share, okay, and please your presentation, please. Thank you.
You unmuted me. Thank you.
Yes, yes.
Okay. Good afternoon, everyone. My name is Julia LITOFCENKO. I work at the Institute for Nonprofit Management at the Vienna University of Economics and Business, where we are repeatedly faced with the problem that there is no public statistics about the third sector in Austria, as in most other countries in the world. And therefore, we tried to look for ways to map the sector according to area of activity in other ways. And this is what I'm going to present today. So here you can see the proportions of the third sector for Austria. We have 90,000 non-profit organizations compared to 350,000 companies. So the third sector is not at all negligible. But probably because there is no money, no taxes involved in most activities of the third sector, there are no systematically collected public data on the sector. I collected some examples to give you an idea of the range of organizations that populate the third sector. It's on the one hand sports clubs, culture and arts associations and social clubs, but also social service providers and membership organizations. Also interest groups and political organizations and professional associations. So you can see those organizations are very different and have a very important impact on public life. And the variable that we were most interested in is the area of activity. And to map the sector according to the area of activity, we relied on the registry of associations, as this is the most comprehensible source of data. Associations are the most common legal form of non-profit organizations in Austria. Associations make up more than 99% of all NPOs. The problem with this registry of associations, as you can see here, is that it's not publicly available and it's not digitized. But we were able to obtain a copy from the registry from a business publisher, Kompass Verlag, that collects this data for financial institutions. They needed to make sure that the legal representatives of an organization can make financial transactions. And this copy contains the association's name, address, founding year, and legal representatives, but no bylaws or mission statements. So mission statements would be highly desirable, of course, as they lay out the activities that the organization performs. But we don't have mission statements, so we had to work with the association's name only. And this is very common for most countries, where you can hope to get some lists of organizations, but no more information. The area of activity is defined, or we define it as the International Classification of Non-Profit Organizations, ICNPO, a classification scheme that is internationally comparable and well corroborated. It's similar to the NAZA classifications that probably most of you are more familiar with, so based on the economic activity of the organization, and it includes 12 major classes and various subgroups. A common starting point for a task like this, so classifying 90,000 organizations, would have been to use a machine learning approach. Approaches like that have also been shown to achieve good results in classifying organizations according to their area of activity with large training samples or long high-quality texts. But we soon realized that in our case, we are in some kind of a catch-22 dilemma, or as we say in German, the cat bites itself into its own tail. We don't have a large training sample, and this is the reason why we need to classify the organizations to begin with. So it's very time-consuming to manually code organizations to construct a training sample. For example, we manually coded 5,000 organizations, and this took us already 100 hours. And the machine learning models we trained on those, then 60% of 5,000, so 3,400 cases. The best model classified only 50% of the NPOs correctly. So it's not possible to work with 50% sensitivity. That's why we soon tried to look for other approaches. The second problem with the long texts, as I said, we only had the names. We also experimented with the Bing search API to get additional information on on the NPOs, but it turned out that the quality of Bing snippets is not very good, so it was much too noisy to train a model on it. I've given you here a table of the performance metric of manual human coding. This was used to establish a benchmark to get a training sample and also a test sample on which we could evaluate the performance of the other procedures we tried. And to remind you that also with human coding is not flawless. So with human coding, we achieved a sensitivity of 85% on average. So after giving up machine learning, we tried a rule-based approach. That is, we manually set up a system of if-then rules. If the association's name contains the word fan club, for example, then the association is classified to category social clubs. And in the end, we came up with 3,000 search terms that are hierarchically arranged in 200 tiers. And what turned out to be very useful in setting up those rules were wildcard lists. So for example, lists of all sports or professions or countries to define rules for certain kinds of associations. Like you can see in the bottom left of the picture, the pattern friends, country adjective is a pattern that goes to the category political associations. The whole syntax and files can be seen here at this address. The core is a very simple grep L command within a for loop. So if the association's name contains search term XYZ, then the association is classified to the ICNPO category XYZ, and if not, then the association stays in the basket of yet to be classified names. With this rule-based approach, we were able to correctly classify 85% of the associations, so comparable to the performance of human coding. And in the end, we thought, well, 3,000 search terms, and we ordered them manually. So probably a decision tree algorithm would improve the performance by finding a better ordering of the search terms. So this way we could combine the best of both worlds. We call this approach then decision tree with curated keywords, where we reduced the noise within the association's names and kept only those parts that we used before in setting up the search terms. But surprisingly, it turned out that this approach performed inferior to the rule-based approach. We had a sensitivity of only 77%, which highlights that those decision tree algorithms are of limited use yet when it comes to high-dimensional optimization, which you easily face when working with text data.
Julia, you have 2 more minutes. Thank you.
And there I am at the conclusion already, that nonprofit organizations can indeed be classified based on their names only with those rule-based approaches. We obtained a sensitivity of 85%, as said, not inferior to human coding and not inferior to classification based on mission and program statements. And it's the best, or respectively the only possible solution in most real-world scenarios. As I said, in most countries, you are lucky to have lists of organizations and no more information. And we tried to use our classification system for Germany as well, because it's the same language, so very easily transferable, and achieved similar results. And it should be an overseeable effort to copy the system to other cultures and other language systems. And the surprising learning was that the classification based on a manually generated rule set is superior at this point in time to a fully automated decision tree classification. Thank you very much.
Thank you. Thank you very much, Julia. As we see, altogether, academia, universities are very close to official statistics, and we can join our forces, let's say, to have good results. So if there are any questions from the panelists or from the other participants, Julia, did you find some nice R packages in order to improve your work, or you think about to search on specific packages, maybe?
No, not really, as this is such a simple, so the R part was very simple in this case, but still very useful for us to have a mapping of the sector in the end.
Okay, thanks. Okay, I will invite also the participants to address questions to the panelists, to author of the presentation, and also the panelists to answer to the Q&A through the chat here in the WebEx platform. So thank you very much, Julia. We will go on to the next presentation. So I think the next presenter, it will be David Salgado from Statistics Spain, with the presentation Selective Editing of Categorical Variables with Random Forest, Results of the Implementation in the Statistical Production. So, David, please, the floor is yours. Unmute your mic. Good.
I would like to use the complete, let me see. Okay, so can you see my presentation right now?
Yes, full screen. Okay, thank you.
Okay, full screen. Thank you very much. Thank you,
David.
Cyprian. I would like to begin by thanking Alexander and the rest of the organizing and the scientific committee of the conference for giving us the opportunity to share our humble work with her in Statistics Spain. My name is David Salgado. I work as a methodologist at Statistics Spain, and this is joint work with my colleagues from the Health Statistics Unit at the Statistics Spain and from the some distinguished members of the IT department. This is indeed a kind of a follow-up of our contribution to the last edition of this same conference, in which we have been able somehow to move closer to production and to test our original ideas in selective editing using random forest with health statistics, with the health interview statistics. Probably for those of you also already working in statistical offices, you know, you are probably very sensitive to how difficult sometimes it is for us to move our ideas and to our proposal to productions. And in this sense, I would like to very sincerely express my gratitude to my colleagues at the production units for this opportunity to test these ideas in real conditions productions. what I want to share with you today is a very short description of what the production process is with these statistics in Spain. It is the Spanish branch of the European Health Survey. I will very shortly explain what is the methodological bottom line to use these ideas for selective editing. Then I will comment on the implementation, and then I will show some of the main results that we have obtained in these experiments, and then I will close with some conclusions. We have tested these ideas, as I mentioned, in the Spanish branch of the European Health Interview Survey. It is a household survey collecting more than 500 variables. To test these ideas, we have focused on a very important variable for the subject matter expert, which is the occupation variable. It is a categorical variable in which the interviewer, in which the respondents provides his or her occupation, right? We use for this Spanish adaptation of the International Statistical Classification of Occupation. It's what we call our national classification of occupation. It is more detailed adaptation of this international classification, as I say, more adapted to our labor market. The kind of estimator that we use are the usual class total linear estimators, in which we just use, let's say, a kind of horizontal estimator in which we finally calibrate weights in the usual way. In Spain, the sample size for this survey is around 20,000 statistical units. And two questionnaires are administered, one for the household and then another one for a randomly selected adult. In the traditional production process, the editing phase basically amounts to conduct a systematic interactive manual editing of each questionnaire, taking into account any other nuclear socio-demographic variables, such as the age, the gender, the professional situation, the economical activity, and the income interval. In this way, Statistics Spain usually contracts editing clerks, which are specifically trained for this survey, and they follow very strict guidelines decided by the subject matter expert. So in this sense, for what I'm going to explain, you can consider this traditional procedure as some kind of as a golden standard for editing, right? Now, in production, the data collection is run, and we receive data every week. So we receive weekly batches, which are then loaded into the manual, into the system, and then are subjected to these editing clerks to follow all these guidelines and to revise and correct the errors. And now for this experience, what we have done is we have introduced a new production step in which, using random forest, we basically provide a prioritization of the statistical units for this manual editing. This new pipeline is not fully integrated in the traditional production system. It is somehow executed also weekly, but in a parallel system, and providing this kind of information to the original system, attaching to each unit the prioritization for each editing in this manual work. In this context, basically the methodology that we have followed is methodology that we proposed some time ago, based on an optimization approach for selective editing. Basically, I do not include here the optimization details. I only focus, and I like to call your attention on the starting point, which is our computation of local scores as conditional expectation values of a given measurement error model, as you see on the bottom of this slide. And then, depending on the kind of model on the target variables, which you see the raw values and the true values, if they are continuous, we can recover under a given asymptotic regime. We can recover at the top of the slide on the branch, on the left branch, the usual heuristic approach, in this case, the easier choice for a traditional score function. But if we use a more sophisticated model, again at the bottom, now for our categorical target variables, then what we propose is to adjust decision tree for the error, for the measurement error, and indeed to use random forest to compute finally the probability of measurement error for each of the statistical units, right? If we also consider the sampling weight, then we can, in a natural way, under this proposal, then we can assign a local score to each statistical unit. For the implementation, the target variable is what the subject matter expert called social class, which is just a grouping of different codes of classifications. We use as predictors different variables already contained in the survey. We use the package random forest to adjust the random forest. To train the random forest, we used some historic data sets of both the European Health Survey and the Spanish Health Survey. And as we progress in our, on the editing work, we also incorporate the on-course already edited data sets, right? And then we apply these trained random forest models. We apply this to the collection of questionnaires not yet edited, so that we can prioritize the units according to the suspicions of error in the occupation variable. I must mention that for the first two accumulated batches, which amount to more than 5,000 units, all questionnaires have been manually edited, right? Not taking into account the prioritization for these first two batches, everything has been manually edited. I must mention that the collection batches, since the systems are not fully integrated, the collection batches and the editing batches are not exactly the same, and that the traditional editing computer system is complemented with this additional pipeline by providing the editing priority, a flag whether it is already a revised unit or not, a measurement error probability, and the item or local score for each of the units, right? As I told you, the first two accumulated units have been manually edited, all of them. For the intermediate batches, according to the results, we only needed to edit the first half of the model selected sample, and in the final batches, indeed, well, in the intermediate batches, the second half, the experts already selected some of them just to check that we didn't leave any error in the non-revised units. And in the final batches, only just the first half model selective units have been revised. Regarding the results, different aspects of the results, we are still analyzing this. Regarding the quality about the prioritization of units, for each of the weeks in which we have been producing or training and fitting the random model, the random forest model, we reach on average about 70% of the area under the curve, so that the prioritization provides already some kind of information about where the errors are, in which units you find the errors with higher probability. I must say that the model is not optimized in terms of the regressors, and probably in the future we can still further research on what kind of regressors we can keep on including in the model to increase this area under the curve. But for us, the priority was to test this idea in production. We have also take a look at the relative pseudo bias for each of the for this variable social class and for each week, and we see that the pseudo bias is immediately reduced according to the according to this prioritization. There are some exceptions, for example, for the fifth social class, in which we still need to take a closer look to the reason why we don't identify clearly this the errors in this class.
David,
yeah.
I think the time is running up quickly, so please conclude. Thank you.
Okay, I'll go directly to the conclusions. Errors have been ranked first. We have been able to check it. We see the errors have been appearing up to a point in which no more errors are in each revised sample. We can also have some measure about the importance of variables. And finally, I can say that we have reached an effective prioritization of the units. And personally, I'm convinced that a collaboration of subject matter experts, methodologists, and the IT experts is absolutely fundamental. An important idea that I've learned from this experience is that instead of going for a fully optimized mathematical or statistical methodology, sometimes it is better to go with a simple model, go directly to production, take your conclusions, and then keep on improving. Regarding the software development, we used a package that you can find there in my GitHub account, but it is fully dependent on the internal ecosystem of our data representation model in Spain. So it is not very exportable. Let's say our wish is that we can mimic the validate ecosystem for data editing in the future. So that's all. Thank you very much.
Thank you, David. We have one question. You partially answered to that question. Did you validate the results against the tradition, meaning the manual editing approach? The question comes from Thomas Berg.
Especially in the first 5,000 units, everything was traditionally edited in a manual editing, not taking into account the results of the random forest. And then we could compare the prioritization provided by the random forest and the results of the manual editing. And indeed, what you see here in these two first batches is that the errors were ranked first. so that we can be rather convinced that the random forest is identifying those units with measurement errors in the first place.
Okay. Okay. Thank you. Thank you very much for your presentation. Very nice presentation. And
Thank you.
We think that in the future we can use their idea and also your package. Thank you. Thank you very much, David.
Thank you.
So next we have another very interesting presentation. Esther, Eustache, I will change now the presentation to Esther. Yes, now you can share your presentation. The presentation is about balanced imputation for Swiss cheese non-response.
Okay, so
the floor is yours, please.
You can see it's okay?
Yes, it's okay. It's full screen. It's everything okay. Thank you.
Okay, so hello everyone. So this presentation talks about an imputation method for dealing with a particular type of non-response that we have called Swiss cheese non-response. This method has been developed by Audrey-Anne Vallée from the University of Laval in Canada, and by Professor Yves Thier and me from the University of Neuchâtel. So we will begin with an introduction in order to briefly introduce the non-response, and especially the Swiss cheese non-response, and some notations. In the second part, I will just explain the imputation method. And then we have developed an R package that is already available on GitHub. So I will finish by showing you some error codes to show you how using this package to impute datasets containing NA's values. Okay, so the non-response. So a little introduction. So suppose that you have a sample S of size n of individual for whom we want to observe G variables to obtain a vector xk. So for example, the height, the size, the weight, or the number of children. And then some of your collecting data are not usable or missing because, for example, people didn't want to answer to some questions. So you can thus divide your sample in two subsamples denoted by SR and SM. The first one corresponds to the respondents. So it's when the vector xk is fully observed. So and the second one, SM, is for the non-respondent. So for these individuals, you have at least one missing values or not usable because, for example, the individuals didn't want to answer to a question. Okay. So this gives two different samples, SR and SM. So the Swiss cheese non-response. So there are different types of non-response depending on their structure in the dataset. So what are the characteristics of the Swiss cheese non-response? So the Swiss cheese non-response is first not monotone. This means that there are no pattern between the NA values in the dataset. And the second one is that the Swiss cheese non-response is contained in several or all variables. So the non-response is multivariate. Okay, so the idea of our method is to generalize a method which is only for the univariate non-response that has been developed by Hassler and Thier in 2016, generalize it to the multivariate case. Okay, so just a little illustration. So suppose that you have a slice of Swiss cheese with holes. Holes correspond to the NA values. So this is the univariate case. And now we want to generalize the method for the multivariate case, so a Swiss cheese with holes. Okay. So the particularity is of the Swiss cheese non-response is that the non-response can be in all the variables of the dataset. Okay. So the notation. So suppose that you have a sample S of size n, as
before, and you are interested in G variables. So here G is equal to 3 at the right of the slide, and you want to obtain the data sets here, okay? But you have some missing values. The missing values are filled in light gray. So you can divide, as explained before, the sample in 2 subsamples, SR and SM, okay? So when you want to impute a data set, you have to satisfy some properties. So the first one is that you have to impute by realistic values. The second one is that you have to preserve the distribution of the variables, and you have also to preserve the relationship between the variables. Okay, so to satisfy the requirement, you have to respect some requirements in our method. So the first one, we choose a donor imputation method. So by choosing a donor imputation method, the relationship between the variable will be preserved. So here in the little drawing here, you can see that E is a respondent, E is a non-respondent. So the respondent will give its values to the non-respondent, okay? So the second one is that each donor should be selected among the k-nearest respondent of each non-respondent unit. So the respondents that each non-respondent will have a respondent to give its values. This respondent will be similar to the non-respondent, okay? And the third is that it's a balancing constraint. This constraint is if the observed values of the non-respondents were imputed, the total estimate of each variable should remain unchanged. Okay, I will more explain this constraint after. So the first step of our method is to compute an imputation probabilities matrix. So we denote this matrix by psi. Okay, so in row you have the respondent, and in column you have the non-respondents. Okay, so the element psi uv is the probability that the respondent u gives its values to the non-respondent v. Okay, and as explained before, only one respondent will impute a non-respondent. So this implies that the sum of the column of the matrix C will be equal to 1, okay? So to respect to satisfy the previous requirements, we have to have some constraints on C. So the first constraint, as explained before, is that the sum of the columns of C will be equal to 1. The second one is that only the nearest neighbors of each non-respondent will have an imputation probabilities larger than 0, okay? And the third is the balancing constraint. So this balancing constraint can be writing as this equation, okay? So here you have the imputed value of xvj, okay? And you have to satisfy this equation, okay? So steps to obtain final matrix psi. So the first step is you have obviously to initialize the matrix psi, okay? So by 1/k if the respondent is in the nearest neighbor of the respondent, and 0 otherwise. And in step 2, you update the matrix psi using an algorithm of calibration proposed by Deville and Sarandal in 1992 in order to satisfy the previous requirements. Okay? So when you have your imputation probabilities matrix, you want to obtain the final imputation matrix. Okay? So for example, the elements here, so in the second row and in the first column, means that the first non-respondent will be imputed by the second respondent, okay? So to obtain this matrix, we have used a stratified sampling method such that the columns of psi correspond to stratum, okay? So we want to only select one only one respondent per non-respondent, okay? And the matrix C respects the previous requirement as the matrix P, sorry, respects the previous requirements as the matrix C, okay? So the balancing constraint of requirement P is also satisfied for phi, okay? So we have developed an R package called the Swiss cheese, okay? And with these commands, you can download this package, okay? So I will just show you a little example. So suppose that you have a data frame denoted by XNA, okay? So here there are the non-respondent units, okay? So SM, the sample SM, subsample. And here you have the subsample of respondent, okay? In the dataset. So as you can see here, the data set of only the non-respondent. So here is the non-respondent, and for each non-respondent, there is at least one missing values in the vector xk, okay? And here you have the respondent, okay, in row. Okay, so you just have to use this function to impute your dataset. So the first parameter is the data frame with missing values. Here you have the sampling weight. So the number of neighbors k, you can choose the value, or if k is equal to null, the optimal k to obtain a solution to the previous equation will be chosen. And here the tolerance parameter, and here the maximum, the number of iterations to consider convergence of our algorithm. Okay, so here you have, after applied this function, you have the optimal number of neighbors because k is equal to null. And here you have the non-respondents, so you can see that there is no NA values after the function Swiss cheese input. Okay, so thank you for your attention. So a little bibliography.
Thank you, Esther, for your presentation. Good timing and very animated presentation. Also very well presented the theory of your work. Good, thank you. So let's see if we have some questions. So I have one question for you. Which you consider that will be your plan for future development of your R package?
Sorry, I don't understand.
Which will be the future steps in developing the R package?
Oh, I will submit to CRAN. I think in the following weeks, and the paper will be also submitted to a journal about this method.
Good. Thank you very much.
Okay. Thank you.
So thank you to all participants being with us at this very nice conference. We hope next year we will see face to face. In any case, we will see next year in the next conference. So I think now I will pass the presenter mode to Alex in order to introduce first lighting talk. So Alex, the floor is yours if you want to present the first one. Good.
You see my screen?
Thank you. Yeah.
Okay, so just
I think it's a full screen, but with two screens because it's very long.
It's not yet full screen before, because if I start
okay.
full screen, then the 20 seconds will count also
Okay.
for me.
Good, good. Thank you.
In short, the next presentations will be given with an automatic switching of the slides. It will be 20 seconds per slide. Between the talks, there is also one slide like the one you just see, so like stating the title and the name of the person who's the next speaker. So that's basically the time you can switch your microphone on, and with your first slide, you can start talking. So I will switch to full screen mode. And I hope you see now the presentation full screen, right? And with that, I would hand over to Matthias that he can start his presentation. In 20 seconds, it should be his first slide, or less than that.
Well, thank you very much. I'm Matthias. You already saw my name and you saw that I work for Deutsche Bundesbank. And more specifically, I work at the Research Data Center. Why am I telling you that? It's important because that's the reason why I spend time on our package for disclosure control in the context of research data centers. This is joint work with Tim Becker, who's also in the audience. In order to understand the package, you need to understand a little bit about what a research center does, and which is what we do is we provide formally anonymized data to researchers, and we do that in a secure environment. So researchers don't have internet access and they can't get the results without the help of the staff from the RDC. And the RDC staff needs to check if there's any confidential information within the results from the researchers. So one important aspect here is that the researchers are in charge of providing all the information that and to show us, the RDC staff, that their results are not confidential. And this is where RDC-log comes into play. It provides utilities to help researchers show that their results comply to our rules. The rules are not that difficult here. The package comprises two simple rules. The first one is that each result must be based on at least 5 different entities. And the second rule, which is also known as a dominance rule, states that the largest 2 entities must account for less than 85% of a result. The second one mainly applies to descriptive statistics, the other one more generally. So this is a theory. Next step is to dive into a small example. Here we have an example data frame. There is an ID column which identifies the entities in this data frame. We have the variables sector and year, some factor variables for grouping, and we have some value variables, val1 and val2. Now suppose you are a researcher and you want to calculate the mean for value 1 grouped by sector. This is how you could do it using data table, which is also used under the hood of sdcLog. And now you need to show me as a RDC staff member that these results are fine in terms of confidentiality. And this is you can do with the function SDC descriptives, which is part of the sdcLog package. And you provide the data frame, the ID variable, value variable, and the grouping variables. And hopefully your output complies to the RDC rules. Obviously, this is not always the case. In this case, we grouped the calculation by sector and by year. And as you can see, we have some disclosure problems. For example, in the sector year combination S1 and year 2019, there are only 4 distinct IDs. Apart from this, you can check your models for disclosure control, and you can calculate non-confidential minimum and maximum values. which is also helpful for descriptive statistics. But why is it called sdcLog? Here you can see the basic workflow we've implemented at our research data center, and it works as follows. Researchers code their analyses in R scripts, and within these R scripts they need to implement and they need to use the functions mentioned before, like SDC descriptives and SDC model. And then they feed these scripts into the function sdcLog from the sdcLog package. And sdcLog is basically a wrapper around the source function, and it writes everything from inputs, outputs, messages, warnings into a log file. And this log file is used for manual checks for confidentiality by the RDC staff. So that's the reason it's called sdcLog, because it's centered around these log files. So if you're interested in this work, get in touch. You get from Ciran. You can install the development version from my GitHub account. You might want to follow me on Twitter or review the slides, which are also available on GitHub. And thank you very much, and I'm happy to hear from you.
Thank you very much. The next presenter is Oliver Reiter from Vienna Institute of International Economic Studies. So, Oliver, please take the floor.
I'm here. Good afternoon, everyone. Welcome to my lightning presentation about an R package called Riot that I created and maintain. My name is Oliver Reiter. I work for the WIEW, which is the Vienna Institute for International Economic Studies, which is placed here in Vienna. The Riot package contains functions to deal with supply and use tables, as well as input-output tables. All functions are implemented in RC++ Armadillo, because the resulting code is both easy to read and very performant. And the functions were used in the creation of the world input-output database Riot. Supply and use tables are matrices with a product dimension in rows and an industry dimension in columns. The supply table states the output by product and by industry, as well as inputs by products. And the use table states the intermediate consumption by product and by industry, plus final consumption by product. So let's go over some usage examples that will show how you can use the package or what the package can do. Even though the examples are very stylized, I hope you will get a rough idea what the functions can do. First, obviously, we have to start by loading the library. In the beginning, we create a supply and use table object using the R6 object system. This object is essentially just a list of two matrices, the supply table as well as the use table, plus some metadata. The class also defines its own methods. A common issue is that the supply and use tables are reported at more detailed level than the available national accounts data. By supplying a vector with a more aggregate classification, we can replace the tables by new, more aggregated tables. The centerpiece of the package is the function to update and rebalance supply and use tables to given national accounts data. Supply and use tables used to be published every 5 years. And as we need a time series of supply and use tables for the creation of an input-output database, we have to fill the gaps by interpolating, backcasting, and forecasting them. We use the Sutras algorithm. This algorithm finds a supply and use table that is structurally similar to the given one, but conforms to new industry level data. And the input to this algorithm are the gross output and intermediate consumption data on industry level. Finally, we can transform the supply and use tables into input-output tables. The Eurostat manual on supply and use tables lists different transformation types, 2 of which are implemented in Riot and shown here. And with that, we have created in 4 steps a time series of input-output tables that matches a given international accounts data. Furthermore, Riot contains several other useful functions, such as the general RAS or GRAS algorithm, which can be used to update and balance matrices to new row and column sums. This is an algorithm proposed by Junius and Osterhagen. An input-output matrix can also be seen as a weighted graph, where the industries are the nodes and the transactions between the industries are also the edges between the nodes. And I implemented a random walk centrality measure proposed by Blöchel and co-authors that calculates the most central nodes in such a network. So the presented RIOT package presents a layer of abstraction for working with supply and use tables, which is very valuable when you're working with a large set of countries and years. Additionally, the implementation in RC++ significantly reduces the execution time. The RIOT package is developed on GitLab. You can find the link here. Please also have a look at our research institute's website, as well as the homepage of the World Input-Output Database project. And finally, there's also a link to my blog where I explain some of the RCPP implementation and details. With that, I'm already at the end of my talk. Thank you very much for your attention and see you soon.
Thank you, Oliver. Thank you for your presentation. Very nice. And I think the next one, it will be with 4 authors, but the presenter is Jörg Verhaeghe from Federal Statistical Office Germany, from DESTATIS, classifying the country of birth using supervised learning. So please, Jörg, your floor.
Welcome to my talk on classifying the country of birth. I'm going to introduce a small project, joint project from the machine learning unit with the migration statistics unit of the Federal Statistical Office Germany. Now look at our little migrant Paddington here. Where is he born? That's the question we wanted to answer, while the German migration authorities do report scarcely on the item. But what they do report on is the country of origin. So where does he enter Germany from? The nationality, date of birth, religion, and place of birth. With the item place of birth being the strongest predictor. But place of birth is a free text item with no additional checks. So consider here the entries from Mumbai, which would lead to the country India, which we found in the data of 2017, which we used for training, to see all the issues with spelling, historical names, and so on. To answer the question, country of birth, we tried 2 approaches, a lead file-based deterministic approach and a supervised learning approach. The lead file-based approach would have at its core country place file and use deterministic rules to figure out which country would be the important one, which would lead to lead file maintenance problems. The supervised learning approach, on the other hand, would make lead file maintenance obsolete, but would rely heavily on the quality of training data. The supervised learning approach used n-grams to vectorize birthplaces just to mitigate spelling issues, and we tested naive Bayes and random forest, and random forest is bigger here because we quickly chose that one because it led to better results. The results here based on data from 2018, while we trained on 2017. The first row is the most important. We had almost half of the items were missing, and both approaches were able to classify consistently. And if you add to them the affirmative cases, we would in both cases have more than 90% new or affirmative classifications, but there is one main difference between both approaches, and that's the classification of the item unknown. The supervised learning approach doesn't do that a lot, and it doesn't do that a lot because it didn't learn unknown in the training data. We don't use it there. So now for production, we needed to integrate the method that we would like to use into a rich client infrastructure, a Java-based one where we would have to do all the calculation on client side. Keep that in mind. Because the Red Fighter, our lead-based approach, worked well. System integration would be easy because you only would have to load up a small chunk of code and a relatively small file, but lead file maintenance remains a job. A supervised learning approach worked as well. Lead file maintenance would go out the window, but system integration was a nuisance because we would need to load up R to all the client machines, which was not feasible in that little project. So in the end, mainly for the ease of integration, but also for the slightly better results, the Red Fighter, the lead file based one wins, but the second fighter, the supervised learning approach, still plays a role in lead file maintenance. Sorry.
Thank you very much for your talk. Now I will invite Solveig Bjørkholt from Statistics Norway. Now you are presenter, so please share your screen.
Let's see here. Hey, do you see it now?
Yes, please go to display settings and put it only on one screen, because now you are on presented.
Exactly.
Yeah. Run the presentation and yeah, duplicate slideshow. Good. Thank you.
Great. My name is Ola Bjørkholt. I'm from Statistics Norway, and I'm going to talk about unstructured text as a source of information. Yeah, right. And why is this important? It's important because it's the world of data out there. And actually, every one of us have generated 1.5 million terabytes of data every day in 2020. So that's a lot. Well, a lot of it is social media, it's YouTube, it's web pages, but also a lot of it is in archives and it's in books. And this is the source of data that we try to tackle in our case. So whenever you try to tackle a problem of that sort, you're going to have an issue with formats. So the issue we try to tackle here is, well, we have a TIFF file. That's a picture. A picture is worse than a TXT file, and a TXT file is worse than a PDF, and a PDF is worse than an XML. And we realized that because these are different degrees of structured data. A picture is not structured at all. Text is somewhat structured, PDFs a bit more, and XML is perfect. What we were dealing with initially was an archive with scanned pictures. So this is important information. People used it a lot to access that information, but they had to go through the information manually and read it as you would a document. And as we realized this, we looked at it and thought, but no, people can't work like this. We have to get this data out and use it in statistics. excited about it? Well, the first thing we did was we looked into a optical character reading method, and we found tesseracts. It's a machine learning algorithm developed by Google, and it's available on GitHub, so it's an open source, and it's very good. It's better than the one we had initially. So the process to and to use and reports, and what we got was TXT files. So now we actually had text information. Okay, but text is just so good. You can only come so far with it. The next thing we wanted to do is we wanted to get from text to table, and that's when we used R actively. And we really used common data wrangling packages like dplyr, stringer, stringy, and rubidate, and we used regex a lot because we had text. So we used white space and line shifts and stuff like that to get it from a bulk of text, as you see here, to a table. And you could transport this table to an Excel file, and it would be useful. But even better, when you have a lot of data, is to put it into a database. So that's the next step. And we had a lot of annual reports, so this seemed reasonable. And then we used packages like dbplyr and rsqlite. And we've also thought about using Elasticsearch, which also has a wrapper in R, because it's a search engine and a database in one. And this way, we were able to take all those text and tables from the annual reports and put it into data. That way, it was way more accessible to people. But what about the people who aren't as familiar with querying data and with programming languages in general? The solution here was to we made an app using R Shiny, and we also used data table to speed up the functions within the app. And then we used Docker. It's an R package, but it's a great way to containerize your app once you've made it, so that you actually deploy it so that people can use it afterwards. And then you don't have to pay. You can do it on your own server. And that way people could access the information that we built just in their own browser. And I do have a demo example here. There you can see in their browser, they can just search for a company name, and there you have it. This is in text, so you can search for things like tax, for example. And then you have the note. This is the gold. People were really looking for this information. They read through it manually. Here, they can just go in, search for a note, and there you have it. And we also try to parse the tables so that they can easily see what the table is telling them. We also joined it with other data and XML files. This is a lot more structured, but it's great to have it in one place. And since it's all in one place now, you can actually search over all the annual reports at once to see if they contain a word, and then get a list of the reports that contain that word. And that's it. Use the data out there. Thanks.
Thank you. Thank you. We want to thank you to all the participants. And now, thank you, Alex. I will give the floor to you to close the session and close also the first day of our conference. Thank you.
Thank you very much. I have not prepared a great closing speech, but I hope you will be back tomorrow. We will start at 10 o'clock with the keynote by Matthias Temper. And we will have at 2 o'clock again an afternoon session. So thank you to all presenters from today, and I hope to see all of you tomorrow again. Thank you.
Alex, one more. We invite also to all participants to send the paper in order to be published if they want to be published in Romanian Statistical Journal. After the conference, it's a deadline for, I think, January. Good.
Good point. Yes, thank you. So 15th of January, until then, you have the possibility to publish in the special edition from the Romanian Statistical Review for this conference.
Good.
Okay. Have a nice day. Goodbye.
Bye.
Bye. Thank you, Alex.
Thank you very much.